always a bit of sentiments, you know. There were certain parts in my life when I went to Budapest 6 to 10 times a year, and colleagues to see friends and colleagues in Budapest, and colleagues from Budapest did the other way around too. Actually, we sometimes had meetings in Bonn, but we only had people from Bonn and from Budapest, and there was a quite large pool there. Right now, I have to admit, my last visit to Budapest was a couple of years ago, and when I walked along the Danube today, actually I have to leave today already because of some accident at my institute, but when I walked at lunchtime along the Danube, I felt I have to change this habit to come only every several years, but so I promise I will come back again. Yes, if you go a bit later into coffee break, it's not my fault. As Bernhard already mentioned, when Anders invited me, I made up a title about multi-commodity and mean cost flow problems from VLSI design. But very recently, we got some results which are quite strongly related to the Hungarian method, so I changed title and contents of the talk. And as already said, it is the Hungarian method and VLSI placement. Since the old abstract was wrong, I will give you just the essence. We talk about placement of large ships, and usually this placement is done in 2 steps iteratively. First, we minimize the quadratic object function, which is pretty large, millions of variables, and we produce a non-disjoint placement, and then you want to make it disjoint best possible. Best possible means to partition the non-disjoint part into parts, and we'll talk about this with minimum changes or minimum changes. This, if we look at this problem in a different way, then it turns out it is a kind of multi-section approach, and indeed a transportation problem in a special diagram, which is heavily unbalanced, and we are using this fact in order to get better algorithm as the best one known so far. Our algorithm has complexity O and log n, and the best known so far was kind of clear to the end, and that is actually the contents of the talk. See, when we talk about chip placement of large microprocessors or logic chips, we should discuss it a bit in the context. We should not only talk about placement, and we talk about only a tiny part of placement, but we should talk about so-called bond tools, which consist by now of millions of lines of codes on routing, on placement, on timing, on cycle optimization, on gating, on blocking, on inverter tree optimization, and so on and so on. During the last somewhat 10 to 15 years, more than 500 very complex logic chips have been designed using bond tools, among others Deep Blue, which against Kasparov lost U3, which is the system controller of the new Apple generation. Actually, even I found out that the routing of the famous Blue Gene chip was done with bond tools. Of course, bond tools have opened also several new areas of research in combinatorial optimization and provided the basis of many new theorems, which is not as easy as making up theorems by just working in a theoretical environment. I will give you some, at least 2 or 2.5, 3 new theorems I will talk about today. We are going to write a book on the mathematics of VLSI design, but since our book on combinatorial optimization was a good book, to do several years, much more than we expected. So I assume the other main story to write about mathematics of VLSI design will take us quite a few years from now on. Well, what shall I mention too? Bond tools have proven the usefulness of non-trivial mathematical practice. Of course, this needs a proof, or it needs an argument here, so there are some dots in it. I try to give you an argument with hand waving. See, of course, Doing microelectronics, people want to be faster and faster and faster. They want to have the gigahertz chips, they want to have multi-gigahertz chips, and so on and so on. They do it, they can do it by changing technology, having a more aggressive technology. Copper instead of aluminum, silicon and insulator, strained silicon, and all these tricks they use. In order to do so, they usually have to do a new fab. And everybody knows to have a new silicon foundry costs about between 3.5 and $5 billion. Mathematics can prove sometimes to gain about 20% roughly, 20-25% by such a new technology. If you use only mathematics, you can sometimes prove that you can also gain 20-25%. And of course, you have investment zero, a bit of thinking only. And then I mean by usefulness of non-trivial mathematics. If you want to have a more detailed proof, I can give you just one idea because we're talking about timing. See, a chip is a quite tactful object. You have certain latches, storage units, and there might be several 100,000 on chip, and you have a graph on those nodes, and the flow of information, data goes from one storage unit to the other. So these storage units you may consider as double doors. One side of the door is open, the information goes in, stays there for a while, and then all of a sudden all doors of those double doors, the other doors open and they travel again. And of course you have to control those opening and closing of the double doors by clock signals. So in order to gain, and of course it is evident for you if the signals travel from one double door to the other one, the longest path between two double doors determines the cycle time and determines whether your PC has a gigahertz or 1.6 gigahertz or 2 gigahertz, because this is actually the longest path between two double doors. So if all the design is already done, can you improve, so to speak, the longest path, that means the time to be used between those two double doors, without changing the whole logic, without changing the whole design? Yes, you can do by optimally opening and closing those double doors, not at once, but slightly shifting. This is actually an application of what Lex mentioned this morning of minimum in-cycle contraction or deletion. So it's another nice application in this area. And by this you can gain, in addition, say 200, 300 picoseconds, and 200 picoseconds of less than a nanosecond is of course more than 20%. And that is the proof that by mathematics without building a factory of several million dollars. Well, this is then the proof. Well, I should also talk about the commercial value of quantum tools and the dollars in it, but I didn't want to be too specific. But here, there was a rumor about some licensing of quantum tools. I heard licensing to Magma Design Corporation, and there was a 3-digit million number involved, so you can get at least a lower bound. It's a limited license, limited in time and in scope, so you can get at least a lower bound which answers in this question. And moreover, it also, to some extent, that those quantum tools have not only provided ground for many new theorems, but also for funds to the Research Institute of Discrete Mathematics and so on. Again, I don't want to be too specific. There are some dots in it, but I can say right now we can run the institute on the interest of those funds, not on the funds, which is a quite nice accident. Well, I don't want to go into details about chip design too much because I want to talk about the mean-cost flow problem, but I want to show you some figures. This is the design placement of a chip, actually of a server, for an IBM Z series. Well, it should go like this. This is the corresponding routing on it. So those are macros, these are caches for instructions, for data, or special cores, special units. And the other tiny stuff, they are little Lego stones, several billion, 5, 7, 8 million Lego stones, which you have to place appropriately in order to route them afterwards. And the final picture on this is actually, if you get then that ship afterwards and you take a microscopic picture of it, it matches one-to-one with the design. This is a quite nice accident where sometimes you as a mathematician can be quite interested in it. But if you don't see the exact matching, I'm willing to show you which are the differences. These are our house. Well, so let us concentrate on just one issue on placement. In placement, we do have a macro placement. This is the first step. I don't talk about this today. We do have what we call a global placement. I will talk about part of it, a small part of it. We will then have afterwards a global placement and relaxation. We have so-called congestion-driven placement because it's not only to minimize the possible net lengths when you do placement, but to avoid congestions that you get a feasible solution at all. You have to have a performance-driven placement, you have to have a time-driven placement. I could add some more lines in it, but I don't want. So let's talk about global placement. There are different methods for global placement. I can't resist making some remarks on the very first lines, because, you know, there are a lot of people who still believe these are the greatest methods in the world, which evidently don't have a theory, but only some relation to some behavior in some other areas, like annealing in physics or genetic algorithm. See, probably 10 years ago, famous Nobel Prize winner Manfred Eigen came to my seminar and told me, look, you're pure optimizers, combinatorics, why don't you look at nature? Nature has done everything efficiently with mutation and selection. That's called a genetic algorithm. And you should do it the same way and then you are done. But nobody has told us how to do mutation and selection for a very specific combinatorial optimization. Or how to tune the screws in simulated annealing. Or probably I can give you some other examples I like to do. See, if you want to cross as a pedestrian, crossing a very heavy traffic crossing, say like Place de la Concorde, and you will do it by simulated annealing, the probability that you will be killed is very high. What do you do instead of this? You take the topology of this very special crossing in consideration and build on this a very specific algorithm, and you are safe by crossing. But I mean, if you, all these general approaches, there's a lot of philosophy in it. Actually, a lot of people worked on placements. There are simulated annealing codes for huge groups in Berkeley that did it for years and years. Right now, the complexity of ships I'm talking about, you could set up a simulated annealing and go home for the next 10 years. So it is certainly not the right approach. There's another approach, a mean-time approach, which is also heuristic. So you take a ship, you subdivide it into parts, and you look at the correction from one side to the other, and then you take one. Those little Lego stones are called circuits. So if I use the name circuit, I mean these little Lego stones. You take one, if I solve it with another from the other side, can I minimize the nets, the lines going across this cut? And if so, I do this. If not, I don't do it. There are sophisticated approaches to this mean cut. They were reasonably good, except, and now again it's a bit of a philosophy in it, you know, placement is a two-dimensional situation. You have to place and to play. Mean cut is a one-dimensional strategy. You clean up the very, very one-dimensional line, probably very well. However, you might cause a lot of problems on both sides of the line, which you didn't have control of. So for this reason, mean cut is not yet used anymore in ship design. There are certain analytic places which can't handle too large issues, and then this one place, which I'm going to talk about. This is a kind of meta description of one place algorithm. Let's read. Let's read those lines. C is a set of circuits, the huge set, million of objects. R is a set of regions, and for the time being, our ship where you want to distribute your circuits. For the time being, there is a R to be 4. And C of R are the circuits of the region. Then one place goes more or less like this. You take an initial region, which is the whole ship. You solve quadratic optimization. You minimize the quadratic objective function. Euclidean distance action. which goes very fast by doing the gradient method, basically seconds. And then, of course, while the window is big enough, you try to partition it into parts of it. I'll show you after the pictures. Then you solve this quadratic optimization problem only on those sub-windows. You do a bit of repartitioning, you do legalization, which is joint, and partitioning we did so far into 4 regions due to some work which Jens Fieging did on his PhD dissertation actually. We partitioned are into 4 regions, and then we used partitioning into subsets by using the so-called American map approach. So this is a rough idea about the whole sketch of the placement. So again, you solve, you minimize correct objective, Euclidean distances. You don't get disjoint placement. You try to make the disjoint by partitioning into regions by a minimal move. Then you concentrate only on those regions and you continue for a while. See, this quantity section was used in one place and with some other places too for a while because it had a nice approach. So given a non-legal placement of circles somewhere in the plane and capacities of the 4 quadrants of the plane, we want to distribute the circuits to the quadrant meeting capacity constraints. The capacities do not only depend on the size, there might be macros blocking certain parts of the region. We want to distribute circuits to the quadrants meeting capacity constraint and minimizing L1 movement. This works only for L1 movements. And Fieging proved that there exists an almost optimal solution by using numerical maps. That means only subdivisions of this, and this pattern might happen. He called it American map because only in North America you have maps between states which have this kind of border lines. So that was a linear time algorithm. And what is meant by almost integer optimum solution, I have to focus on it too. Almost integer meant the solution is integer up to 3, only 3 objects can be fractional. How this 3 comes in, I will tell you in a minute, because an extension of this theorem is used in what I call, from now on, a multi-sectional answer. That is, was the basic of it, and quadratic section looks like this. You start it, say, those macros have been placed first. You start it, and the colors indicate. Of course, this is not the amount of Lego stones, because they are piled up here. They are not disjoint, so it's not the real measure of the amount of Lego stones. It's just a picture. You see here the American map, and yellow means it should go in the upper part, blue means it should go here, red means this and that, and this is by minimum of movement of L1 distances. Here's another picture. So and then it continues. I want to give you an idea of the whole algorithm. So that was quadrant section at the first step. Then, of course, you concentrate. You move those blue objects into that region. You subdivide that region into another 4 objects. You get again a quadrant section. You move this. You continue like this, and continue until you are almost in. If you want to know what it means, I can be more specific on this. I should mention what repartitioning means. Of course, you might probably have done, when you do this partitioning, the wrong partitioning at some time, and then you can never get rid of it. Yes, you can. You move with a window of different sizes across, put everything together, and do repartitioning again. That helps a lot in order to improve the quality of the placement. So, very last picture on the old one place is this one. Again, this is the first step. Actually, there are certain objects at the boundary, I/O paths or so, and for this reason, otherwise, if there would be no forces going to the boundary, then the minimizing of the Euclidean distance would just be piling up into the center, or something, because that would be the shortest distance at all. So those are essential in a sense, because that helped you afterwards to spread out the old stuff and continue like this, and eventually get a legal placement. Well, the new approach is different. Why only partitioning into 4 regions? Why only partitioning into quadrants, which are said? Take arbitrary sized regions, even not only rectangular, take more than 4, and call it a multi-section problem. Multi-section problem is defined like this. You take a finite set of circuits, you take a finite set of regions, you have sizes for each circuit, of course they have different size, you have capacities of each region, you have costs for the moving from a circuit to a certain region, and of course your task is to find a mapping which fulfills the capacity constraints and which minimizes the total distances. Here we do not talk only about L1, we can also talk about Euclidean and other distances too. Fine. This multi-section is evidently has something to do with the assignment problem. Yes, generalization of the assignment problem. If C catenate is equal to R catenate, it has L1 and L1, then you have exactly the assignment problem. To decide for a feasible solution for this multi-section problem is already complete. And moreover, which I already mentioned, we are interested in a heavily unbalanced bipartite graph in such a sense that we have millions of objects, but you want only to have 9, 10, 12 or 15 regions. So the first relaxation is that you can do not a multi-section but a transportation problem, which of course gives you a fractional solution, but on this I will get back to when I said almost integer in the other case. So, transportation problem, we do have a directed bipartite graph with the source and the sink. We have the usual edges, we have capacities on the incoming edges to it's almost an uncapacitated problem, except on the incoming and outgoing edges we have capacities which are either the size or then we do have costs. We can normalize the distance function by the size of a certain object. We might not do it, that is up to us. And the cost of the incoming and outgoing edges are 0. In addition, what we do have supply and demand values at the vertices, but we do have only this supply value at the source, the whole size, at the sink, the whole size. All other supplies are 0. And of course our task is to find the minimum cost flow in the flow network and cost. If you want to have it in a picture, that is the problem. Large instance C, small instance R, no capacities on the arc of the bipartite graph, capacities here and there. Of course you can get rid of the capacities at all by the old Fulkerson trick, which doesn't make too much of a difference in the size of the problem. And of course then we have to use a mean cost flow problem. Of course you all know there are different approaches for mean cost flow. There's the minimum mean cycle cancelling algorithm, where you have always a feasible solution which fulfill the B flow, but you continue to minimize the cost on every negative cycle. As long as you have negative cycles, continue, it will not be as. The successive shortest path works a bit differently. You have always, in every step, you have the mean cost solution, but it is not the right B value, so you are approaching iteratively the right B value by taking path between certain nodes S and T. And of course, then this is very slow, and this capacity scaling was the first approach in order to make it faster by not taking the minimum amount on the shortest path, but only consider shortest path between two nodes which are above a certain capacity, but above a scaling factor, and that works too. All in then improve this not only by capacity scaling, but by proving that certain edges shouldn't be considered at all. Our algorithm is in that line of a successive shortest path algorithm, but a bit different. Well, We search for a minimum ST flow, that means maximum ST flow with minimum cost, of course, minimum cost of flow. A flow in this network corresponds to a fractional solution of the multi-section problem, which we started with, of the same cost and vice versa. That is trivial. That we probably shouldn't read because I will come to it in another slide. So question, what other approaches have been done so far? There are papers by Tokuyama and Nakano in 92 and 95, where they got an algorithm like this. And you will fix k, which we will do in any case because k equals 9 is k fixed. Then you come up with this complexity, special cases for k equals 2. We have a fractional Nash problem. It's known there's a linear algorithm on it. If you have all sizes of c equals 1 and capacity from n, then Tokuyama and Nakano again came up with an algorithm like this. Well, by Tartan I can skip for the time being. For bottleneck objective functions, Hochbaum and Wigner got the linear algorithm. That is correct. And now let me concentrate a bit on solving this problem. The fastest strongly polynomial algorithm for the general uncapacitated are this, by Long, by Hornig. This gives for the transportation problem this complexity for k less than n, this, and for k constant, that complexity. Kleinschmidt and Schanheit improved it again for k less than n, that means our problem to n squared k log n. Then Matsui came up with an algorithm which he claims for this complexity that would have, of course, a linear algorithm in our case. However, this approach is wrong. There is a definite counterexample in the meantime, by this counterexample, that this algorithm is wrong. So again, the fastest algorithm so far is that of Tokuyama and Nakano, which is basically O n k squared log square n. Did you see a bit? And of course, if we have k fixed, then it is of this complexity. We will improve it with that complexity, and if we fix k, actually is a sorting which goes in, which then causes this complexity only. And of course, we make use of two facts. First, G is bipartite, which is known, of course, and k is very small. An algorithm is, as I said already, based on successive shortest path approaches. Now this almost integer comes in, and again it's a different slide but the same context. So directly the solution of the transportation problem, and for every circuit in that large group, we define by tau fz the number of arcs which going out of C which are positive, which have a positive flow. And ff is then the number of C's where the flow is the number of arcs which have a positive flow is greater than 1. Those are the fractional ones. Yeah, because you split up the flow into different ones. And now this lemma, which gets improved for the quantum section only, for this, can be generalized to this, and it's saying given an instance of the transportation problem and an optimal solution, then there exists, then you can find in that time, which is a nice time, an optimal solution with the two properties. The number of fractional vertices is less or equal than k minus 1. Remember when we had the quantum section k was 4 and I said the almost infinite resolution is 3 fractional variables only in it. So again, this is then small even if k is 12 or 16 compared to millions of it. So the relaxation of the multi-section of the integer version to the transportation problem doesn't harm us too much due to this result. And that is because if you have millions of objects which are properly placed, integerally placed, then the very few ones which remain fractional. You can just do by accident or by throwing a coin or whatsoever. Well, so now it is up to me to give you an idea how modification of the successive shortest path method will come to an algorithm of O n log n. Of course, this is a brief sketch of how this successive shortest path algorithm works. Initially, you start with a zero flow. You have your objects, and what you actually do, as long as the flow does not satisfy the capacity which is put on, you find the shortest CIT path in that graph, and you augment F along that path by the minimum of this. This is the original, and of course, this might cause a lot of problems. Please keep in mind we call this a phase of the algorithm because I will make use of this phase later on too. Of course, I think that what I already mentioned, we can make use of those two facts. Sorry, that was a double equation. And what do we have to solve now? Two problems. First of all, the number of augmentation can be exponentially limited. If you would do just a very plain successive, you can just do increment by one, all these nice examples work here too. And then of course the exponentially limited side. And moreover, each augmentation must be computed in the incremental graph, which is G sub F. And this incremental graph is as large as the original graph, even larger because you have arcs in two directions if you do the implementation on this. So, how to overcome those problems? The strategy in general is as follows. First of all, we solve the circuits according to non-increasing size. Then we set the set of augmentations that increase a flow is called the ice phase. I already mentioned that. And let f I minus 1 be the flow at the beginning of the ice phase. And now we show during the phase, at least I will give you some rough idea about this. During the phase, the flow has to be changed only that much. See, there is no n in it. Moreover, we can replace all augmentations in a phase by a single minimum cost flow in a quite small graph, in a graph which does not depend on n neither. And those two facts are essentially in order to get an improvement of the running time. So again, some notations. You consider only the phase I. Each element of the surface belongs to exactly one of the three following classes. Either to zero vertex, no flow goes out, so it's not moved. It's an integral vertex, if this is the case, or it's a split vertex, if this is the case. But remember, there can only k minus 1 split vertex. That is what we have to keep in mind. And then the successive shortest path algorithm goes like this. Instead of working on the whole incremental graph gf I minus 1, which is as large as the original graph, we work on a graph gi, and this graph I'm going to explain to you. This is a subgraph of the residual graph, which is induced by a vertex set xi, and this vertex set xi contains only the following vertices: r, small, 1, 1, and those are the split vertices. I write it down here again, are more precisely the objects Ci prime with Ci prime less than I, such that there exists a vertex Rj with this flow below the size, and then of course Ci belongs to that vertex set. This is one group, and the last group is a bit more complicated, and actually this set. Am I running out?
Yes, I think we're ran out.
32. Good. Okay. Those are the vertex sets, and this is a bit more strange vertex sets. You get an artificial vertex in it for this vertex, which you might move from region Fine, those are the vertices. The edges I don't explain to you. And the result is then the following lemma. During the augmentation phase, only edges in this graph, which depends only on k. And so this is this dem fast, dem small, have to be attacked. And then it is very easy. You have to sort, remember, O n log n. You have to augment, that is O n log k. And then you have some k's in it, k to the square. So altogether, it comes up to the complexity I mentioned. See, I'm really speeding up. So we got a new algorithm, which is n log n. And it does now multisection instead of quadrisection. You have, for instance, here 9 regions. It gets much better results. And moreover, it's surprising, you know, the quadrisection was a linear algorithm. But this one, in practice, even runs faster, at least half the time. And by this trick, we could speed up the whole placement running time by a factor of 2. Comparison. The quadrisection, of course, is theoretically worse than the multisection is theoretically worse than the quadrisection, fine. But there's a better running time in practice. It's applicable to any fixed number of regions, and for this we get a much better placement. Regions do not have to be rectangles, they can be, and you don't need to concentrate on L1 norms, you can concentrate on different norms. Again, all these slides are not shown. You can improve running time, but at least some of those slides I wanted to show. Improve running time, you improve quality of the results substantially, you can do a bit of forward-looking partitioning. At least I wanted to show some comparisons with other placement. You see, there was a competition. Usually you don't know what the optimal solution of the placement is. You can only get an idea of how close you might go. Even you won't get precise lower bounds. There is no way to get this. These were problems posted up in the literature where they didn't know the optimum solution and they disturbed them heavily in order to get then the solution. And then those are 6 out of, or 5 out of many other approaches. And this is the factor that are apart from the optimum. 2.53, 1.62, 1.84, 1.97, and so on. We run those problems also on with bond place, and there are 3 different ways according to how we partition. I don't want to go into details. The best you can get, you are 60% of the optimum. There's another test case series which I don't want to go into details, so I skip them all, where there were practical problems given to other placement algorithms, and they had, I think, a week time to run with any computer, even with blue G or what do they call it, to get a solution. And they had to publish it after 5 days, all praying to God in order to get a better solution. Nobody asked. They got only a limited amount of time. We didn't participate, of course, and that's the competition. We solved them afterwards, and we got evidently better results for all the test results. And this is actually the very end of my talk. I should mention Ulrich Brenner, a student of mine. Most of the practical results I know this, and Jens Wiegenberg. Thank you very much.
Are there any questions? So I think Andras has been computing online the time that we come back after coffee. But can we thank Bernhard again? Hard schedule, I would suggest that we would have a 25-minute break now, so we continue at 5:20. 5:20. If this is okay, that's it. So everyone. No.